copy it. Oh, good. Now I can do that. This is my directory, so you move here. There we go. Now I'm going to copy this file. Let's see. Let me delete this. No! How about that? It. Okay. Now I can go and change it. Okay, so we went through the MVP. So I'm going to copy this MVP now to Brandon. Okay, but before we start the molecular dynamics simulations, what is always recommended is to do an energy minimization. Remember about energy, so to move particles just a little bit to relax the energy. Okay, what could happen is when you add waters and when you added hydrogens, it might cause certain atoms to overlap. Okay, if the atoms overlap, imagine the amount of energy. Okay, even the van der Waals energy goes up as 1/r². So it's very high energy. So if it's a very, very high energy, you're going to get a very high force there, and which means even for a 2 femtosecond time step, the change in position that you're going to get will be very high. If there's a very high change in position, you're basically causing the whole system to explode. so you might it'll say, oh, the whole protein exploded, and then you look at the PDB file, all the atoms will be apart. So you want to do is before you run a molecular dynamics simulation, by default energy minimize so that you remove these bad contacts. Okay, so I have these energy minimization files also in there. I'm going to copy this one to Brandon. Okay. So what does the energy minimization look like? It's a very, very simple file. Okay. Much simpler input as compared to what was before. You have the energy minimization integrator, which is steepest descent algorithm. Okay, set it to that. How many steps of energy minimization you want to do? I say just 1,000 steps are enough. Okay. You want to put any constraints? No constraints needed. And this is energy minimization stuff. So what is the tolerance on the energy? It's 1 kilocalorie or 1 kilojoules per mole. The step size for doing energy minimization, this is 0.01 nanometer, just 0.1 angstroms. So the maximum step that the atom can take during energy minimization is 0.1 angstroms. You can do it very slow. Okay. Again, you set periodic boundary conditions, X, Y, Z. Okay. And all this is again R Coulomb cutoff, R van der Waals cutoff. Okay. There is no need, there is no temperature, there is no pressure, there is no velocity. Okay. So now you have this input file here, which is EM H2O Okay, so this is all the input instructions. You have the coordinates here, okay, and you have the topology file. So now, at this point, what you do is you combine these 3 files together to create an executable for molecular dynamics. Okay, and the way you do this is use a command called GROMPP. Okay, so this is nothing but GROMAX pre-processing. Okay, so it needs an input file. So for pre-processing, the input file is actually the MVP file. which is em h2o.mdp. Okay. You want an output file. Okay, the output file. I usually use the same name for the output file, so it is em h2o, and the type of output file is actually called the TPR. Okay, so there are various different file names that you would have gone through today. You'll start remembering them. Okay. Minus F, minus O. Okay. We need to supply the coordinates. The coordinates are supplied using minus C. Okay. And then the topology is supplied to minus P. There are 4 files. It's going to be 3 inputs, 1 output. At the end, it's going to give you this emh2o.tpr file. Okay, hopefully done. Into LS. Okay, trying to copy this. Okay. Right? Got it? Okay. Since we have the TPR now all you have to do is you have to use this command md run. Okay? That's basically standard command run motion dynamics. In this case, it's just an optimization. Okay? And then you can write the name of the output file, and you can supply all that. But what I always do is I use minus def and then. Okay? So this is basically default name. So whatever is the name of the input file, all the output files have the same name, but different extensions. So you know where it was created from. Okay? And this is em/h2o. You don't put any extension on it. So when you just give it the default name, it's going to automatically know that the input is this.tpr, the TRR file is going to be this.trr, XTC file is going to be this.xtc, right? So that's the default name. All right, and you go, it optimizes. Okay, so it did not run for the entire 1,000 steps. What it tells you is sequence descent converts in machine precision in 92 steps. Okay, but did not reach the requested maximum force of 1. Okay, always make sure that the potential energy is negative. So this is a pretty high negative number, minus 1.9 to the power 10 to the power 5. Okay, if it's a positive number, it means something went wrong. You should never have positive energy. You should always get negative energy. Okay, this was the maximum force on atom 332, norm of the force. Okay, then you have some other stuff here. So now on the 92nd step is where the optimum structure is. So you want to now pull that structure out from the trajectory file. Okay, so when you ran this, you created all these files: emh2o.edr, okay, emh2o.log, trr, okay, emh2o.trr, and you also created emh2o.grow. That is basically the last snapshot. Okay, but you can also extract the last snapshot from this TRR file. Okay, so that is what we're going to look at now. Okay, we have 10 more minutes. If we have 10 more minutes, then we can, because after this we just have to do one more CompBio and we can start the MD simulation. We good? Right. So if you want to extract anything out of the trajectory file, the command for that is scratch conv. Scratch convert. So for scratch conv, the input file is emh2o.trr. Okay. And this TRR file, this is actually a binary file. Okay, there are two kinds of files in Unix. One is a binary file, one is an ASCII, ASCII file. Okay? ASCII files are human readable text files. Binary files are all in zeros and ones. Okay, yeah. So it's much easier to, if you're running code and you want to extract things out of a binary file, it's much faster than extracting things out of an ASCII file. Because if you read an ASCII file, you have to convert it to binary, then do all the operations, and then take the binary information, convert it back to human readable form. Okay? So this TRR file, if you can open it, it looks like matrix, zeros in one flow, right? Exactly what this TRR file is. So it's much more compressed. Okay? And this TRR file, if you open it, all that it contains is atom indices, coordinates, velocities, and forces. Okay, they're columns. It doesn't have any information on atoms. Like I said, every atom is now tagged based on its index, right? 1, 2, 3, 4. Okay, but all the information that you want, but in the end, what you want is a PDB file that you can see, right? So the PDB file also has information on atoms, residue types, and residue numbers, and everything. So this by itself is not going to give you all. This is going to give you is atom index followed by XYZ. But if you want the PDB file, you want to give it a -s option. Okay? And that -s option tells it all the information necessary to create the PDB file. And all that information is really in the TPR file. Okay? The TPR file has everything inside it. It has all atom names, it has the force field, it has everything that is necessary to run the molecular simulation. Okay, so you give it a -s option. So here it's going to extract all the nomenclature information. Here it's going to extract the coordinates. Okay, and you want to dump out the last frame here. Okay, because it optimized in 92 steps, you really want to dump out the 92nd frame from there. Okay, so I'm going to say minus dump 92. Okay. Right, and then I want to give it an output. And this output is basically going to be model 1, rename PDB to GMX, SVC, and in the end I put EN. So I know after I put the SVC, I energy minimize it. Okay, if you want to store more information as to how many steps it ran optimization for, just put 92. Okay, so just by looking at this file name, I can tell what I did to it. Right? It doesn't matter how long the file name is. It's just much easier to store everything this way so you know what you did to each file. Okay? And you run this, it will give you this option. What do you want to dump out? Do you want to dump out the entire system? Just the protein minus the hydrogen, C alphas, backbones, you can dump out whatever you want. Okay? Because all this file, all this information is really in the topology file. It knows what is the backbone, it knows what the C alphas are, it knows what non-protein atoms are, it knows what the water, the salt, and everything is. Okay, it's really cool. And so you really want to dump everything out. So you select 0, and there you go. Okay, so that's now your input file for doing the molecular dynamics. Okay, so now you have a file ready to do molecular dynamics. You can use the same topology file, but now you use a different MDP file, and that is this one, 0 to 100. Okay, so it's the same process. You're going to do a ground PP, minus P topology file, minus F, which is the 0 to 100 nanosecond file. Okay, minus O. We're going to call it a minus O.tpr file. Okay. Minus C is this model 1 that I obtained from energy minimization. Okay? So for completeness, what we're going to do is we're going to go through the same process once again next time. Okay? Right from the start. And I'm going to go through it a little faster. We're not explaining every little thing. So we're going to go through the same process again, but next time we're going to add ions to it. Okay? Just one extra thing. Is that cool? Okay? Make sure you do go over the homework. It will be easier to understand the concept. Alright, so when you do this, it has even common from Pulp Fiction. There it is. Okay. So now this creates this 0 to 100 nanosecond.dpr. Okay, and you can run this job. And it begins to run. Okay, so what it's using is it's making 2D domain decomposition. So it's basically running this on 16 cores, 4 times 4 processors. It's running this on 16 processors, and it's going to take a couple of days to run, maybe a day to run, to get 100 nanoseconds. Okay, now you can't do that. As soon as you log out, the job is going to shut itself down. So how do you do that? You use something called a queuing system. Okay, so you submit your job into a queue, and once the queue finds the number of processors you need, it's going to assign them specifically for your job, and you ask them what a specific amount of time, and it's going to run that job on those cores, and those will be dedicated to your job. Okay, so if I do a Control C at this point, I can cancel this NV run. Okay, if I cancel it, I always run it a little bit just to see whether it's running fine or not. Okay, and so I did a Control C, and you get this. So on 16 cores, it's basically giving you 27 nanoseconds a day. Okay, but these are the cores which are on the head node. So it's not like I'm the only one using them. Many people are using them together. So that's why it's slower. You can generally expect to get 50 nanoseconds or twice as more of this based on if you run this remotely. Okay, and how long has this thing run? So if you look at this log file that got generated, this is all the input, and this is where the log file really begins. Okay, so you have at time 0. Okay, it prints out the energy in kilojoules per mole of angles, dihedrals, Coulomb, Lennard-Jones. This Coulomb recip is the Coulomb reciprocal space, so that is beyond 10 angstroms. Okay, and then it's spitting everything out every 1,000 steps, which is basically every 2 picoseconds. Right, so the time now is 2 picoseconds. It gives you this 4, 6, 8, 10, 12, 14. So it basically ran for about 17.45 picoseconds. So as soon as I press Control C, it printed out the last one. Okay, so that's how it ran. So it ran for over 17 picoseconds. So in order to submit this job into the queue, there's this little script here. So you don't need to submit it now. I'm just going to get this thing to run until next time we're going to look at it on Tuesday at 1 by 10. So we'll copy this submit script. Okay, so this is what the submit script really looks like. It has a job name that you can give. I'm going to call this job name. It's a very short one, plan. Okay, I'm going to ask for 16 processors. I'm going to ask for 70 hours. Okay, and then it's going to load certain modules. Okay, what module do we have to load to run GROMACS? Do you remember? Module load apps.nomax or right, so that's what we did. So it's going to load that module. It's going to change the directory. That is the current directory, home SSO Franklin. So it's going to run the job in that directory. And it's going to use MPI run to run MD run MPI. I forgot what it's called. I have to sort that out. Okay. So there are different kinds of MD runs here. Okay, there are at least 4 different kinds. Okay, so this is the one that used MD run before. Okay, and that is using multi-threading. That is, all the processors are going to cores are going to be from the same processor. But you can have cores across different processors. If you want to communicate cores across different processors, you have to use MPI. Okay, so you have to use this word MPI MD run. S is for single precision, D is for double precision. If you do double precision, it's just going to be slower. Okay, so this is the one I'm going to select. UV on MPI S. MPI 1. MPI S. That's it. And the S batch. You submit this job. Job violates policy. That's good. This is a job limit size, apparently. Okay? Which I did not know. This is the student cluster. So maybe this is too big. Job. Which means it's not going to run for 100 nanoseconds. So how about you try 28 hours?
I think it's only for 30 hours.
30?
30 hours.
Just for 30. Okay. Oh. Anyway, I'll sort this out. It should show up, no? It's running. Nothing happened. It ran and then it got killed. There is no domain decomposition anymore for this compatible with the mailbox flows. The number of flows are in the options. It just ran for 16. Why is it not going now? What? Now it's running. So it launched very quickly. Now it's running on 24 process, which is going to run fast, generally. Right? Next time you're going to go through the same process, run it with ions, so to clear some things even more. Okay? And then you'll be able to ready to make mutations. And for mutations, would you prefer to have do this in groups or individually?
Hello?
Groups of 2 or individually? So I'm going to leave it up to you. So you can either do it individually or you can do it in groups of 2. Okay? It's not about points, right? It's worth 15 points is the take-home assignment. But if both of you do it and you can complete it, you still get 15 each. If you want to do it alone and you can't complete it, you go most of it, you still get 15. No?
But that's not assigned like now, right? That's after.
After, yeah, that's later. Right, there is a take-home project, right?
Yeah.
Worth 15 points. That's what I want to know. Do you want to do it individually or do you want to do it in groups of 2? It's entirely up to you. So if you want to select a group of 2, just do that. Because some people like to work together, and if you're working together, it makes it easier for you to keep up things.
Is it going to be? Are they going to be slightly different?
It'll be the same protein,
Same protein.
but with a mutation.
Okay.
That same protein mutation. So just let me know who wants to do alone and who wants to do. Okay. So I can assign the mutations.